Greeting, and today we would like to present about our single-step processor. Our motivation for it is because it is composed of multiple components, allowing for greater opportunity to understand the core concept of a processor. It is also flexible and scalable in terms of its instruction, allowing for continuous addition of instruction, work distribution, and many more opportunity to learn and create each.
Alright, moving on to our main feature for our single-step processor. We have a simple instruction input, which only use opcode, and an optional intermediate, which is like an actual CPU. Next up, we have two internal registers for operand, that is our A and B input, 16 bytes of RAM supporting both read and write, 8-bit simple arithmetic format, which are addition, subtraction, multiplication, and rough division, bitwise operation, and or not, exclusive or logic shift in both the right direction and the left direction. 7 segments for displaying outputs and registered value, and a programmable ROM for autonomous execution.
Or it consists of basic components. Register A, which displays the value at register A, and B, which displays its own value respectively. Ground input as the immediate input, which feeds the value to our given instruction, and the opcode input, which sets what instruction we're doing. For example, adding A and B, setting A, or setting B. As our button here, it triggers the clock or executes our instruction. These 3 LEDs light up in these given conditions. If A is more than B, if A equals B, or A is less than B. So for our example, 139 is more than register F. So see, it lights up.
Okay, so in this section, I'll be demonstrating a few instructions that I think are quite noteworthy of. It's also a good chance to see the board working as a whole as well. So let's start off with trying to read and write to the 16-byte RAM. And the way you do this is that we're going to be writing to a memory address of 5 with the value 15. So in this case, we'll be calling opcode 4, which is set memory at address A to the value of B. So that means that I want to set B as 15, which is opcode 5, and set A as 5. There we go. And then we call opcode 4. And when we press execute, nothing really happens because there's no direct feedback from the RAM, but we can actually verify the execution. So we'll first clear register B, and then we'll call opcode 3, which is going to be setting A as the value in memory address of A. And we press execute, we got 15, or F, which is what we've just wrote to memory address of 5. We can also do, let's say, addition as well. So I'll be calling opcode 2, which sets B to whatever is in A. So now we're going to be adding 15 with 15 by using opcode 7. Press execute. I think I executed twice. Hold on. Yeah, that's a bit of a debouncing problem, but you're going to be getting 30, which is 16 plus 14, 30, which is 15 plus 15. Let's subtract again, and we come back to 15 plus 15. We can also do multiplication. This is a one-cycle multiplication circuit or instruction. So we'll be multiplying 15 with 15. You call opcode 18. So we press execute and we got E1. Now E1 is 16 times 14 and plus 1, which is going to result in 225, which is 15 times 15. We also have bitwise instructions as well. So let's do an XOR between 1111 and 0111. That should gives us 1000, which is 8. So let's set A as 15, 15 again, B as 7. Okay, and I'll just kind of leave this to be garbled value. We're going to be calling opcode 11, which is the opcode for XOR. execute, and we got 8, which is 1000, which is what we expected. We can also shift the number as well. So let's say I want to shift the number 8 to the left by 2 times. The way you do this is that you just kind of set B to whatever you want to shift to. We want to shift to 2, so let's set B to 2. And we'll call the shift instruction, the shift left instruction, which is 16, so 16. So what we did is that we shifted the number 8 to the left twice. And when you shift something to the left twice, you're technically multiplying it by 4. So we've turned 2 power of 3, which is 8, to 2 power of 5, which is 32. And this is 20, which means that it is 32, which is what we expected. We can also similarly call shift right to bring it back. So now we got 8. So I'll be demonstrating the autonomous execution feature of the project. The way you use this autonomous feature is that you flick the switch and then you don't actually have to enter any opcodes or immediates. You can just kind of leave them as is, and it will execute purely from the program ROM. But before this, that also means that you're supposed to write your program using opcode and immediates into the program ROM.vhd. You test bench it using the CPU ROM simulate file, and then after you're satisfied with how it's supposed to behave, you upload it to the board. Now, for the project, the program that comes default with the program ROM is the multiplication demo that we'll be doing today. And the way you use this multiplication demo is for the operands of the multiplication, you will be writing it to mem0 and mem1, and the output would be mem2. So memory address of 0 and 1 is for your 2 operands, and the output is at the second address. The program counter, which is on the left here, starts at 0. So this is already set at 0. So the lucky number for today is 14 times 9. So we'll be writing 14 to mem0 and 9 to mem1. So let's write 14, let's set 14 to B. Okay, that's 14. Memory address of 0, and we call opcode 4 to write to mem0. We then set B to 9 and set A to 1. Opcode 4 once again. And it's also a good idea to set mem2 as 0 because I didn't have anything to clear that address. So we'll be setting A as 2, set B as 0, and execute. You can also execute twice, it doesn't really hurt anything. So we're pretty much ready to go. I'll be setting B as some random value like okay, I don't know what that value is, but in theory it should not it shouldn't cause any problems with the execution because the input should be taken purely from the program ROM, and we're going to be flicking this switch. Now as soon as we flick this switch, the board will ignore any inputs from the opcodes and instructions, so I can just kind of leave this as much garbled as I want. So for this demo, we're multiplying a 4-digit value, and each digit will cost around one program cycle, which basically means that you have to wait until the program counter reaches 0 again. So we have 4 digits for the number 14, so we have to wait for this thing to return to 0 4 times, not including this. So we'll start by pressing the execute button, and immediately it runs by itself. We'll be pressing a button for around 160 times. I think that was 1 already. 2. 3. And 4. So we've executed the multiplication for 4 times. Flick this off. I'll flick this now because it does matter. We can read at mem2 by setting a as 2. And let's read from mem2 what we got. We got 7e. Now 7e is, I think it's 112, which is 16 times 7 plus 14. So 112 plus 14 is 126, which is actually 14 times 9. So we got our result. So this should demonstrate the autonomous execution feature of that project. Okay, so I'll be explaining the rough architecture of the CPU module, which is what cobbles every other single thing together. I think it's a lot more simpler than some may think of for what it can do. But the first thing that the CPU would do is that it has to select which opcode and which immediate it's supposed to use. So it can either be from the user's input switches, or it can also be from the program counter, both for opcode and immediate. The way we select this is that we just use opcode 7, which is the switch on the leftmost side. If the switch is on, we use the program counter's value. If the switch is off, that means that we're going to be using the input, which is from the switch on the board. And every other single thing else is actually not really in steps. It just works together at the same time. So I guess I'll be starting from top to bottom. At the top, we have the input going into the byte multiplexer, and it also goes into register A. So what this actually does is that, first, if you want to feed a value into register A, you have to select which byte. And the way you select which byte is that you just use a multiplexer and use the opcode as the selector for that byte. So you're going to get 1 byte into register A. Now, that's the first part, but the second part, you also need to have a conditional check whether that opcode is for writing to register A or not, so that you don't overwrite register A every single instruction, which in most cases you're not going to be writing to register A. And then you have this line which goes out into off the to a module. This means that it's the output of the module. And it also goes into instructions as well. I'll come back to this later. For register B, it also works with it works the same way. We have a multiplexer that selects which byte, and then after that we check whether the register B is supposed to be overwritten or not, and that also outputs register B out to the module as well. So this line right here is the instructions, and typically instructions would use both register A and register B as well. Some only use register A and some only use register B. Some output to register A and some output to register B, so it really depends on each instructions. The output bits also really vary for each instruction as well. Next is the 16x8 memory. Now, this is actually the 16-byte RAM. The 8 means 8 bits. So there are a few inputs. We have register A out as the address. We have register B out as the value to write to that specific address. We also have a check whether that opcode is for writing to the memory or not, which is opcode 4. And we have the clock cycle into the module. And it's going to be outputting the RAM output, which is also used to set register A as well. That's opcode 3. And moving down, we have the section for the autonomous execution feature. And there are a few things happening. We have the program counter, which itself has the value. Now, the program counter is used in 2 things. First is that it's used as the address to access which byte of the ROM, both the opcode and immediate as well, which is what we use for these the inputs. And it also goes into the program counter increment, because every time you run an instruction, it's supposed to increment the program counter, which is here. Now, there's also an input going into the register, which is going to be setting the register to a new value each time. This is selected by final opcode again. So in some instructions, like the jump instruction or the opcode 63, which sets the program counter to the value of A, this is where this would select the register A out as the value. But in most cases, we would just kind of select the incremented program counter because we don't set the program counter using an instruction that often. And yeah, so that is for the program counter. And finally, we have the byte comparator, which is the 3 LEDs you see on the right. We compare between register A and we compare between register B, and this outputs three bits, which is also used for the LED as well. So for the output, we also have the program counter for the output as well. So that is pretty much it for the rough architecture of the CPU. Done.
Go.